Solve problem 10.2 Hanging storefront sign. Suppose the mass of the sign is capital M equals 33.1 kilogram and the mass of the post is small m equals 19.7 kilogram. The length of the post is L equals 2.40 meter and the sign is attached to the post at a distance R equals 1.95 meter from the wall. The cable is attached to the wall at a distance d of 1.14 meter above the post. We need to find what is the tension in the cable and what is the magnitude and direction of the force that the wall exert on the post. So here in this question you have a post which has a length L of 2.40 meter. The mass of the post is 19.7 kilogram. You hang a store sign of mass capital M 33.1 kilogram on this post at a distance of R equals 1.95 meter from the wall, and the cable is attached to the wall at a distance D equals 1.14 meter from the post. And in the first part we need to find what is the tension in the cable. In order to find the tension, we need to use the equation for net torque. And if the post is in static equilibrium, that means the net torque acting on the system must be equal to 0. So I write tau net to be equal to 0. If net torque is 0, that means torque which are counterclockwise must be equal to torque which are clockwise. To find these values of torque, let us first understand the forces producing them. So first you have the force due to gravity acting on the post, which acts at the center of mass of the post. I will call this as Fg1. Fg1 will be at a distance of L by 2 from the wall because it is at the center. Then you have the force due to gravity acting on the store sign, which we call Fg2, which is at a distance r from the wall. Both Fg1 and Fg2 makes an angle of 90 degree with the post. Then you have the tension in the string T making an angle theta with the post and at a distance again L from the wall. Fg1 and Fg2 are trying to pull the post down, so they produce a torque which is clockwise. Tension T on the other hand produces a counterclockwise force. There will be a normal force that the wall exert on the post, which we can call as Fx, the horizontal force, and the force of friction preventing the post from falling down, which we can call as F of y. These two forces exert no torque on the system as they are acting on the axis of rotation. And if they are acting on the axis of rotation, the distance r is 0 and hence there is no torque produced by them. So we will only discuss torque produced by tension Fg1 and Fg2. Now we write torque tau as Rf sine theta, where F is the force producing the torque, R is the distance of the force from the axis of rotation, and theta is the angle between them. So for counterclockwise torque, we write counterclockwise torque is produced by tension T. Its distance from the axis of rotation is L because it's from the other end of the post. So we write this as Lt sine theta equals clockwise torque is produced by Fg1 and Fg2. Fg1 is at a distance of L by 2. So we write this as L by 2 Fg1 sine 90 plus Fg2 is at a distance R. So R Fg2 sine 90. I want to find the tension T, so we divide by L sine theta throughout. We get T equals L by 2. Fg1 we can write as mass of the post into acceleration due to gravity g. Sine 90 is 1 plus R. Fg2 we can write as mass of the store sign into acceleration due to gravity. Sine 90 again 1 over L sine theta. Now we have everything we need here except for the angle theta. Theta is over here and we can find the value of theta using trigonometric ratio. I know the side which is opposite to theta d and I know the side adjacent to theta which is L. So we will use tan inverse to find theta. Because we know tan theta is opposite over HSN. Opposite side is T, HSN side is L. So theta will be tan inverse T over L. That gives me tan inverse. D is 1.14. L is 2.40. That gives you the angle equal to 25.4 degree. So let's substitute that here. L is 2.40 by 2. Mass of the post is 19.7. G is 9.81 plus R is 1.95. Capital M is 33.1. G 9.81 over L sine theta. L again 2.40 into sine of the angle 25.4. And when you solve this, you get tension T in the cable to be equal to 840.35 Newton. Then in the next part, we need to find what is the magnitude and direction of the force that the wall exert on the post. So the force that the wall exert on the post is first the normal force, which we have written the horizontal force Fx, and the force of friction, which we have written here as Fy. Magnitude and direction of the force will be the resultant of this force and its direction. So first we will find what is the horizontal force and the vertical force, and then we will find their resultant angle and magnitude. So we already identified all the forces acting on the system. We have Fg1 due to the weight of the post, Fg2 due to the weight of the store sign. We have the tension T in the string making an angle theta with the post. We can split this tension into two components, one going along the y-axis, which we call as T sine theta, one going along the x-axis, which we call as T cosine theta. Then we have Fx, the horizontal force due to the wall, Fy, the vertical force due to the wall. And when you find their resultant, this will be the force F that we need to find. Now, since the system is in static equilibrium, that means the net force acting on the system must be equal to 0. Net force is 0, that means sum of all forces along x-axis must be equal to 0, and sum of all forces along y-axis must be equal to 0. So let us begin with the x-axis. I write F net x to be equal to 0. F net x is the vector sum of all forces along x-axis. Along x-axis, we have two forces here, Fx and T cosine theta. And when we say vector sum, we have to take the direction into consideration. So forces going to the right, we will take positive. The ones going to the left, we will take them as negative. So I write Fx minus T cosine theta equals 0. That gives you Fx equals T cosine theta. T from the previous part of the question was 840.35 Newton, whereas the angle theta was 25.4 degree. So let's substitute, we get T to be equal to 840.35 cosine 25.4. That gives you Fx to be equal to 759.119 Newton. Or you can round this off to 759.12 Newton. Now we do the same thing to find Fy. We write F net y to be equal to 0. Now there are four forces acting along y-axis, Fg1, Fg2, T sine theta, and Fy. And again we do the same thing when we find F net y, we are finding the vector sum of all forces along y-axis. So forces which are going up, we will take them positive. The ones going down, we will take them negative. So we write Fy plus T sine theta minus Fg1 minus Fg2 equals 0, or Fy to be equal to Fg1 plus Fg2 minus T sine theta. Fg1 will be small m times g, Fg2 will be capital M times g minus t sine theta. So now let's substitute. We can take g common in these two. We write it as 9.81. Small m is 19.7. Capital M is 33.1. Minus t is 840.35. Sine of the angle 25.4. So that gives you Fy to be equal to 157.5 Newton. After we find the x and y component of the force, now we will find its resultant. We know resultant F will be given as square root x component squared plus y component squared, that is equal to square root 759.12 squared plus 157.5 squared. So F is equal to 775.28 Newton. This is the resultant force that the wall exert on the post. Now we need to find its direction. To find direction is to find the angle theta. It's not this theta, the angle theta that we are finding, I will call it as theta 1. It's the angle the resultant force makes with the post. So theta we can find by taking tan inverse. So I can find theta 1 to be equal to tan inverse f of y over f of x. That gives you tan inverse f of y is 157.5 and f of x is 759.12. That gives us theta 1 to be equal to 11.7 degree.